Welcome to the Cosmic Pi Podcast, episode 16, year or series number 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. Robert, do you want to start off by doing a disclaimer so we don't get fired?
Yes. Oh, well, that won't keep us from getting fired. But the opinions and everything expressed herein are those of our Wayne, myself, and our guest. They do not reflect the opinions necessarily of the University of North Dakota, the College of Arts and Sciences. You got to come at us, folks. So.
Now, we do have a live chat feature that's running, so if you have any comments or questions that you'd like to ask throughout the podcast, feel free to use that feature, and we'll stop and try to answer the best that we can. Today, we have a very special guest, Dr. Andrew Knoll, who's emeritus professor now of the Fisher Professor of Natural History at Harvard University. Andy, I don't know what to call you, but I know you're a paleontologist. I know you're a geologist. You've dabbled a lot in biology as well, so I'll let you explain yourself. I know you've won numerous awards. In fact, you are also the author of several books. One of the books I have read already, just to prove that to folks, I'll hold that up to the camera. It's called A Brief History of Earth. And you have a new book that's out now called Earth and Life, a 4 billion-year-old conversation. So, Andy, thank you very much for joining us.
Thanks for having me.
Now, I guess we could start off maybe by defining for those who are unsure, what do we mean when we say like paleontology, and how is that different from like anthropology and maybe some of these other terms that people toss around a little bit?
Okay, well, paleontology is the study of the records of once living organisms, particularly as fossils, which can cover a fair bit of ground. And it's basically everything from, maybe a rabbit skeleton that's 2,000 years old to bacteria that lived more than 3 billion years ago. It differs. Anthropology is the study of humans and our close relatives. And of course, that overlaps with paleontology. If you think of Lucy, the famous fossil in Africa. And then there's another related subject area, which is maybe the thing that's closest to what I do now, and that's called geobiology. And it is really an integrative science that aims to take information from geology and information from biology, both comparative biology and fossils, and try to understand how basically Earth and life have interacted through time to determine, in many ways, the environments that surround us, and they have a very strong influence on the evolutionary history of organisms as well.
So it's fair to say, of course, what you do in terms of your research and others is very multidisciplinary. I mean, need to know about paleontology, you need to know a lot of geology, biology, mix of anthropology, as we mentioned already. But there's more like the basic science, like chemistry, for example. You think of atmospheric science and even planetary science and so on, because I've noticed from your bio that you've also spent a lot of time working on the Mars Exploration Rover mission.
Yep.
So in that sense, I mean, as let's say a young student that's trying to get into this field or very interested in this, there's a lot you got to learn.
Yes.
Well, yeah, I think it's important to realize that geology is really not a way of looking at the physical world. It's the study of an object, which is the Earth. And you could get insights from chemistry and physics. And so people like me would take chemistry and physics courses in college. Obviously, to be a paleontologist, you need to learn a fair amount of biology as well as sedimentary geology. So it is, in a sense, interdisciplinary, but that, to be honest, doesn't differentiate it from a lot of other sciences, in that the 21st century really is the age of interdisciplinary science, where more and more people in more and more disciplines are really improving their understanding by looking to neighboring disciplines and seeing where the commonalities are. So it is the science of the 21st century, I think.
Now, one of the big things, of course, the buzzword out nowadays is AI. AI this, AI that. So would AI help into looking for, let's say, correlations that otherwise may have been missed from research that's been done, like field work and things been done in the past? Is that a fair statement?
Yeah, it probably does. I must admit that I am AI ignorant and likely to remain so for the rest of my days. Um, but certainly, where you have large amounts of just observational or analytical data, I can imagine that AI can somehow, sort out some of the generalities of it. So I think it is here to stay, and let's just hope we can make use of the good applications.
Right.
Right.
Now, is it true, Andy? I get this impression, and I could be totally wrong because it's not my expertise at all. Is that when different researchers go on field trips, they bring back to the museum or laboratory a collection of objects, let's say, but there's usually not enough time to go through everything in fine detail. So you kind of try to do the cherry picking, pick out the best stuff or things that you think are the most important at that moment. The rest of it is kind of put aside a little bit when you have more time, or someone else will go back later and look at those kind of things. And once in a while, of course, you'll find something very interesting. Is that true, how that works?
Yeah, that's more or less true. I think the thing to realize that to a geologist, the rocks that you see out there in cliff faces, road cuts, mountainsides, you name it, those are really the library of Earth history. And so when I'm in the field, I will do what's called taking a measured section. That is, I'll start at the bottom of the cliff and work my way up, describing meter by meter what I see, and then taking samples every meter or two. And you're right that I don't immediately go back to the lab and analyze every sample, but I can tell you that there are samples that I collected 40 years ago that still find application when someone calls me up and says, say, I have this new technique for looking at limestones. What do you got? And that's actually kind of fun to do those kind of collaborations.
It reminds me a little bit about, you're bringing back the lunar rocks and soil from the Apollo program, and only a small fraction of that was ever analyzed. The rest of it's stored in case of increase in sensitivity of instrumentation, new instruments come along, different ideas that can be tested, and you're trying to have a certain collection of pristine material, just in case you don't go back for over 50 years, is what happened.
Well, I think that's right. That's pretty much what happens in earth sciences. I mean, if you do your work, 10 miles outside of St. Louis, you can go back to the places that you sampled, almost any weekend. Now, I've done a lot of work in the high Arctic and Siberia and places like that. And, I'm not going back there. So it is useful to have these samples in abeyance so that when a new technique comes along, you have just the things that people are looking for to analyze.
Right.
You're reminding me, while it was case, Ralph Harvey was working with ANSMET, the Antarctic Meteor Search Group. And I kept going, let me go. Well, I have pretty severe respiratory issues. And so Ralph kept putting me off. And finally he pulled me aside and was like, Rob, we will never let you go. If something happened, he said, I'm like, but nothing's going to happen. It hadn't happened since I was a kid. He's like, if something happened, you're 4 months there and nothing we can do. And I was like,
Yeah.
oh, man. So I get what you're talking about, the high Arctic. You never get it. You've been there, don't want to go back. So, yeah.
One of the things I noticed that was in the Brief History of Earth book is you have a photograph from Mistaken Point from Newfoundland. And
Yep.
I was born in Canada and grew up on the East Coast in Nova Scotia. And so I'm really familiar with Newfoundland. In fact, I have family members who live in Newfoundland. And it always struck me that anytime, and I've been there many times, that anytime I visit Newfoundland, you get that feeling of like the Canadian Shield type of landforms. Like it just feels like it's been around, at least the high rock cliffs and things of that nature. It's been around like a billion years or more. And so, that's the kind of areas you want to look at. It reminds me like Greenland or, like Northern Canada has a lot of, as I mentioned. And Newfoundland is kind of a piece of that, right? It's the old Appalachian mountain range type of thing. So I guess that's
Yeah,
yeah. Go ahead.
I was
Sorry.
going to say, yes, Newfoundland is a combination. The western end is the Appalachians, and the eastern end was what part of what once was another continent that crashed into ancestral North America. So there's a lot of history in those rocks.
Yeah. So some of that life, like the fossils, they date back to what, 500 million years or on that order. Is that correct?
Yeah, I mean the mistaken point has been made, World Heritage Site, and for good reason. You may recall if you've been there that you have not only layer after layer deposited between about 575 and 560 million years ago, but the rocks are sort of on end. And in many cases, you can see just broad expanses of bedding planes. And it's like you're walking across an ancient surface, and it's an ancient surface that's completely strewn with early animals. So you can not only see what they looked like, but you can see more ecological features like how they're distributed on bedding planes. It's a truly spectacular place.
Yeah. I mean, the other thing I think about is life. So the oldest form of life, and I guess you can divide it into complex life, micro, organs type of life, or cellular like life forms, that the stromatolites are like the oldest. That's what I learned, right? And they're up to what, 3.5 billion years old type of thing? Is that?
And stromatolites are not themselves fossils. They are structures that are accreted on the seafloor under the control of microbial communities. So in a sense, it's more like, Robinson Crusoe's footprints than Robinson Crusoe. But you're right. You go back to some of the oldest rocks that we can look at uh, and hope to learn anything, and they're about, 3.5 billion years old, and they're stromatolites, which means there were photosynthetically driven bacterial communities already at that time. Now, when I say already, that's a billion years into Earth history, and there are various biological ways of just estimating when the last common ancestor of all living organisms lived. And most people think that, for the last 4 billion years, Earth has been a biological planet. And that's worth underscoring because people, I mean, you guys are astronomers, you know that people are always asking, you know, how difficult is it for life to begin, and maybe what's special about Earth is that life began here. I mean, I wouldn't be at all surprised to know that life begins under many circumstances, under a variety of plausible conditions. And what makes Earth special is not that life began here, but that it's persisted for 4 billion years.
Right.
That could be truly unusual and really set us apart from most other planets and moons.
Yeah, you might. I reminded myself of the book, The Rare Earth. I think Peter Ward and David Brownlee, I
That's
believe,
right.
are the authors. Yeah. So they make an argument where you have to have all of these things happening in order to increase the probability of complex form of life as we know it to exist here on Earth. And given it's a big chain of probabilities, that it makes it probability-wise that maybe it only happened once. And we know it happened once, of course. We're here to talk about it. But the chance of it happening, like I don't know how you would call it, advanced life forms like human beings existing somewhere else is pretty rare, hence the title Rare Earth. And that would
Yeah,
include,
now,
yeah, go ahead, sorry.
go ahead.
Now, I was just
I
going to
was
say,
just
and
going to
that,
say that
yeah, sorry, you go.
Sorry.
I think one has to sort of look carefully at what we mean by rare. It turns out that, let's say that one in every million planets will give rise to complex life. Now, that's rare. I'll agree with that. But when you think that there are what, 2 trillion galaxies, each one with a billion stars, each star with probably several planets, you know,
Yeah.
one in a million means there should be life all over the place.
Right.
Yeah, and then I would, as a counter argument, I would say what I'm talking about is complex life, not bacteria or viruses or whatever you want to think of, very simple creatures. But to get to the point where you can evolve to have the type of life we have here on Earth, that requires a lot of things. And their argument would be, for example, that you need a moon to provide the stability and the obliquity of Earth's axis so it doesn't tip over periodically and cause huge significant climate change on the planet that potentially could harm life here on Earth. And to have a large planet, massive planet, in other words, in our solar system, like Jupiter, that would act as a clearinghouse, that would attract some of the leftover debris from the formation of our solar system, and then, it would have it go into the Jupiter itself or be ejected from the solar system or find its way heading towards the sun, that would be required, or life would get a foothold, start going along, and all of a sudden, bang, you got like a real mass extinction, as in almost total. And that would occurring over and over again because of, leftover, let's say, asteroids, for lack of a better word.
Yeah, I mean, that's not a crazy argument. The real problem with the whole discussion, to be honest, is it's one thing to speculate, and it's another thing then to go out and actually observe things that can help you find out what the answer is. So, fortunately, in our own solar system, we can go there to different planets and moons and ask questions about habitability. Now, I think, to be honest, the chances are just about zero that there are other, technologically competent life forms in our solar system. But once you get beyond our solar system, we can look at fairly nearby galaxies and stars. But, the best we can do in some ways is look at their atmospheres and try to detect whether the atmosphere may have been formed under the influence of biological processes. Now, that's an inexact science. It's not clear to me that there are actually diagnostic biological atmospheres, but it's something to look at. And really, for most of the universe, the only way we're gonna know about life is if they tell us.
Right.
Yeah.
Good point. Yeah.
Well, I was thinking of the controversy from just a couple of years ago that I'm sure you've heard, where people observed a larger than expected abundance of phosphine in the atmosphere of Venus, and that somehow that was a potential sign of biology. And it caught people's attention, and you're never so sure as, boy, there's a couple missions that are in front of NASA right now for consideration that want to go back to Venus. Oh boy, did this news ever come along at the right time?
No, that's been a very controversial observation. I think whether or not the observation is correct is certainly something that's been discussed. If it is correct, whether or not it necessarily comes from biology, I think a lot of people are in doubt about that. But that just illustrates the nature of the problem. Earth's easy. We have these people who have television sets and all sorts of things that we can project out into space. But, if you had, I hesitate to say nothing but bacteria, because I'm very fond of saying that we need bacteria, but bacteria don't need us. I think it is, uncertain, really, what the limits on biological or bacterial signatures on planets are.
And that brings up a point that I've tried to make, is that that chemical signature in the atmosphere is not going to be one gas or one signature. We're going to need a suite. We're going to need, atomic oxygen. We're going to need these other gases that need to be replenished, and one of their major sources is biological. Now you can start saying, well, yeah, the combination of these things points strongly to life. Any one of them, well, it may be, maybe not. So yeah, I'm one of those proponents that I think that's what we need to start looking for. It's not any one gas, one signature.
Yeah, I have to tell you a little anecdote. One of the people who was, I think, the first and most cogent person to make that kind of argument was the late James Lovelock, father of the Gaia hypothesis. And he argued back in the 1960s, when NASA was just starting to think about what we might look for as signs of life when we went to Mars. And everybody was looking at what we'd find in the soil. And Jim basically said, no, it's easy. Look in the atmosphere. If you have oxygen and methane, which should not exist together in an equilibrium situation, you got life. And one night I was having a dinner with a really very fine planetary scientist named David Stevenson at Caltech. And I trotted that line out to Dave, and he just smiled at me and he says, you know, I can guarantee you that within 6 months of that observation being made, there'll be half a dozen models for how to do it without invoking biology.
Yes.
So, you know, I think we just go make the best observations we can and see where we land.
Well, it's like, wasn't it the mid-1990s, right, where Bill Clinton made a statement about the meteorite that was found in Antarctica with possible evidence for nanobacteria. Remember all that hoopla from? I think
Yes,
that was out of the Johnson Space Center, if I remember right. And
yes, that's right.
Yeah, and being part of
and
NASA gives us some clout, right? If you're associated with NASA.
Well, NASA did a good thing. I think it was actually Al Gore who put it together, but there was a meeting in Washington that I was participated in to ask about not only this material, but one thing that NASA noticed was when you started talking about life, people were interested.
Right.
And so they had a meeting based on, you know, what do we look for? I think, to be honest, pretty much everyone at the meeting was skeptical of the results of that particular meteorite paper. But what it did, it completely realigned NASA's Planetary program. And basically looking at the environments of different planets and moons, looking for evidence of life, became the major things that NASA was interested in finding. So in a sense, even though I'm not convinced that the paper was correct, it actually had a very positive influence on getting NASA to revamp its programs.
I guess that would be in a time where NASA came out with the Follow the Water theme in Martian exploration.
Yeah, exactly right.
Yeah.
Exactly right.
You know, even I remember like in graduate school, so this would have been, I think, in the early 2000s, where there were scientists making the argument that you see up like, you know, like from the Viking days in the 70s, the first photographs, you see dried up tributaries on the surface of Mars, which automatically, because we're so used to living here on Earth, of course, because where else would you be, that you see, that you notice that they're, okay, that's obviously been created by running water in the past, and something happened and the water went away. But then other people said, you know, if you look at it carefully, maybe it wasn't water. Like maybe it was carbon dioxide frost and the general movement of that. And we know, you know, that Mars has polar caps made of that, that with the sun heating it and different heating effects happening, that this stuff will move around on the surface, maybe given enough time, that it would create these kind of water-like dried up tributaries. I mean, that was out there, right? That was proposed.
Yeah, I think, to be honest, most people accept now that most of those channel systems are water. There's a lot of hydrated minerals around, so we know that water was there, at least episodically. I think one of the things that my friend and colleague Robin Wordsworth and I published a paper on fairly recently holds that when you look at the record of aqueous environments and clement conditions on Mars, that it may well not be that Mars was warm and wet for 600 million years and then slowly dried out. It may be that Mars was warm and wet for 100,000 years every 20 million years for the first 600 million years, and then dried out. And that has very different implications for life.
I remember that paper.
Well, I'm just thinking,
reading it in one of our
yeah,
reading groups.
how would you test that?
Well, I think you have a lot of stratigraphy. You have some sense of what the time scales are for the development of that stratigraphy, given the kinds of processes that show evidence of being in play in the rock record. And so at the moment, we can say, well, it looks that way. And then Robin, being a modeler, showed how, if Mars was pretty cold and dry most of the time, but then you whack into it with a big meteorite or have major volcanism, that can actually push you into warmer, wetter conditions, but then they would dissipate through time. So again, it remains a hypothesis, but I think it's as well supported as any hypothesis we have for early Mars.
It would be nice, in the future, and it'll probably be a long time, of course, to go to Valles Marineris, and there's got to be a lot of layering that's directly exposed there. That would be just a gold mine.
Oh yeah. I mean, I think what I learned from the Mars Murr exposition, the one that I was on the science team for, was that if you asked a planetary scientist where they would like to go to land on the United States, they'd say the Grand Canyon.
Yeah.
If you asked an engineer, they'd say Kansas.
Right.
And Kansas always wins because you don't want to make problems for the landing.
Right. Well, you can see, they've had a drone-like helicopter flying around on Mars. I can envision in the future, scaling up those big heights of Valles Marineris and doing detailed studies at different heights. You don't even risk.
It could happen.
Yeah. You don't even need to risk, human life to do that when you think about it.
But, I'm interested in that whole Tharsis plain, that whole Tharsis region.
Yeah, the volcanoes.
Yeah, I want to see the volcanoes.
Olympus
I wanna
Mounds,
see the canyons. Let's look at it all. But
sure.
So let's
Well,
say
the problem, of course, is that there's in the planetary science community, there are Titan enthusiasts, there are Enceladus enthusiasts, there are Mars enthusiasts, and I think a lot of people think, and not without some justification, that Mars has gotten most of the resources long enough, and that maybe it's time now to spend some resources on looking closely at places like Enceladus, which arguably could have extant life in a subsurface ocean. Europa, a moon of Jupiter, which clearly has an ocean beneath its surface veneer of ice. So there are a lot of things to look at, and we don't have the resources to look at them all at the same time. So it's an interesting thing for NASA to juggle.
Yeah, for sure. Nowadays, of course, with the recent, again, budget proposal, it's not a great time to be a space scientist in NASA.
Right.
So,
yeah.
yeah. The other thing too, so Andy, let's say in the future we find some bacteria that's surviving on Mars, and everybody would jump up and down, of course, a great celebration, life somewhere else other than Earth. But how do we know that didn't somehow infiltrate from Earth? Because we know there's a lot of cross-contamination, right? We find, meteorites, obviously the one we talked about already, from Mars. And I'm sure there are Earth rocks on Mars. So how do we know we didn't contaminate Mars, that it was initially sterile and then we brought life there?
Well, the good news is that if Earth bacteria colonized Mars, you could look at their DNA and compare it to the DNA of bacteria from Earth. And if they're basically the same, pretty clearly you have a contaminant. But you're right. I know people who would like to think that life on Earth was basically flown here in a meteorite from Mars. The problem with that is that we have no evidence that Mars ever had a biota to get jettisoned.
Yeah, it almost seems like you'd have to be somewhere far away, if not another solar system altogether. If you find life there, then you can be 100% sure, nature naturally would make this given the right ingredients and opportunity.
Yeah.
Yeah, there's no question that if and when we find living bacteria on Mars, a lot of people are going to be interested. I'm going to be very interested. But, you're absolutely right that if we discover something like that, one of the first questions that needs addressing is, did it originate there? Did it live there? Was it flown there on, the heels of some rover? But that can be known.
You know,
I hadn't thought about that, but yeah, that
Yeah.
could be tested. That could be, yeah.
well, isn't like chirality one of the things they look for, the handedness? That if it's,
Oh, chirality. Yeah.
yeah,
Um, yes. And again, if you have, well, if you have DNA, and you may or may not in life forms from other places, but uh, you do have chirality to the different molecules of life, amino acids in proteins. And if you found that you had the other opposite handedness, and I should stop and just say for your listeners that things like amino acids are not perfectly symmetrical. So they're, in a sense, they're like your hand that has a thumb on one side and your fingers on the other side. And so you can have left or right-handed amino acids, and only one of those is chosen by organisms. So yes, if again, finding amino acids on Mars would not be a big deal, because we know since the experiments of Stanley Miller, in 1950s, that under plausible early Earth conditions, you can make amino acids, and he made them in the laboratory. A number of meteorites have amino acids in them. So I think finding an amino acid is not in and of itself a signature of life, but rather it's a signature that some of the same types of processes that led to life on Earth operated, at least transiently, on other bodies.
yeah, because we've sat, recently we've even heard of reports of amino acids being found on asteroids, like Ragu from.
Oh, yeah.
Yeah.
Others, yeah.
So it almost seems
Yep,
like
that's right.
it's everywhere, right? In our solar system, at least, it seems to be the basic building blocks that you would need for life.
And
Yep.
as we've discussed with other guests, things like micelles, which are bilipid layers, form readily. The ingredients are there. It's just a question, did they all come together at the same time in the same place? And, how you get that all kick-started.
So, I mean,
Yeah.
I think that like the average person doesn't appreciate the history of the Earth to the degree like you yourself obviously know about. It's a lot of people have a misconception that if you go back 3 billion years in a time machine or something, the DeLorean, right? and you walk out into this lush jungle with dinosaurs running around. But that is not the case. Isn't the fact that most of the history of the Earth was completely different than what it is today? And here I'm talking about like the percent of oxygen, breathable oxygen in our atmosphere.
Yeah, I think almost every aspect of the Earth has changed through time. We're used, having seen Jurassic Park, to thinking of fossils as fossils of dinosaurs and things like that. But the oldest animals that we know of from the fossil record appear about 85% of the way through Earth history. Life appears, as I said before, closer to 4 billion years. So what that's telling us is that for most of our planet's history, the life on this planet was largely, if not entirely, microbial. And you're right that, we're used to, in fact, we're dependent on an atmosphere that has 21% oxygen in it. But for the first 2 billion years of our planet's history, there was no oxygen in the atmosphere or oceans. So yes, I mean, in some ways, it's a grand story of how Earth and life have, in a sense, almost co-evolved through time.
Yeah, in fact, if you went back far enough, you would be in an environment which you would perish, right? You wouldn't be able to survive in. It's too hostile compared to what we need today here on Earth.
Oh yeah. Oh, that's right. You'd asphyxiate through most of Earth's
You don't
history.
even have to go back that far
Yeah.
to get to that. So, yeah.
So I guess a question would be, why did it take 85% of Earth's history before we see the arrival of things like animals? Is there a reason for that, or is this natural evolution? It just takes that long sometimes for that to occur.
Well, we since we only have one example, we don't know whether we're a representative or not. But it is pretty clear that bacteria can there are many, many types of bacteria that live in no oxygen conditions, and they can metabolize, they have carbon cycles and everything like that. You need at least a little bit of oxygen to make so-called eukaryotic cells. That's cells with nuclei, like the cells in our own bodies and amoebas and plants, you name it. And then you need somewhat more oxygen to make the kinds of animal communities that we see today. And interestingly, we have 2 billion years where oxygen isn't being produced enough. And I should say that the only source of oxygen that's, abundant enough to transform the planet is actually photosynthesis. And so on the early Earth, which was more or less like a water world, you had volcanoes sticking up, maybe here and there, a little bit of continent, but there wasn't much land sticking out above the surface of the water. And so the influx of nutrients, particularly phosphorus, was low. So you didn't have very much photosynthesis going on. And then, interestingly, about 2.5 billion years ago, that's right before the so-called Great Oxygenation event, where we started to get an oxygen-rich planet, the continents emerge. And that has to do with tectonic history. That is the physical history of the Earth's mantle and things like this. And then you have more nutrients coming in, more photosynthesis. You have enough photosynthesis to basically oxygenate the planet. Now, how much oxygen was there when that event was over? Probably about 1% of today's level. So it was still pretty low, but it was high enough to support eukaryotic cells. And guess what? The fossil record shows eukaryotic cells in rocks that are just a little bit younger than this oxygenation event. But that low oxygen world, again for tectonic reasons, continues till about 600 million years ago. And then we have a major mountain building event that gives us probably the first Himalaya scale mountains in more than 1 billion years. Again, more nutrients coming in, and that brings oxygen up to something like 10 or 20% of today's levels. And that's enough not only to make animals, but to make carnivores, which are major drivers of diversity among animals. And then by about 400 million years ago, there's evidence that for the first time in Earth history, the entire oceans were oxygenated from top to bottom. So it is an episodic increase. It appears to be driven in part by tectonic events in our planet's physical history that have consequences for primary production. And the biggest consequence of these events is that it makes new types of life possible.
So where would the water go then at planet-wide sort of scales? Does it just leaches into the ground, so it's underneath then?
Well, that's interesting. It's a good question. It turns out that my colleague Rebecca Fisher and her student showed very nicely that at the temperatures of Earth's mantle in the interior that we think characterized the early Earth, it was too hot for the mantle to hold much water. So basically, all the water was degassed. Now, if you look today, most people think there's at least an ocean's worth of water tied up in the mantle. And if you push that all out to the surface, add another ocean of water, and there isn't much land going to be found. And excuse me, what was I going to say? So then when you have plate tectonics starting to go, and that takes some materials, sediments and water within them, and takes them back down into the mantle. As the mantle cools off, more and more of that water will stay in the mantle, and that will draw down the water levels at the surface. So again, there's a number of different processes going on. I'm not sure we understand them all fully, but somehow they gave us a world that for, again, not only if the first 2 billion years had no oxygen, but there wasn't a lot of exposed continents and things like that.
And I do want to bring up a point because they ask me about this and get a little confused. When we say there's an ocean's worth of water in the mantle, we are not talking liquid water. It is bound up in the minerals as hydrous minerals, as water-bearing minerals. So, don't think there's an ocean underneath the crust. It's just that all these little rocks have a couple of molecules of water tied up in them, but there's a lot of rock in the mantle. So,
Yes. Yeah. Yeah. I thank you for bringing that up because that's exactly right.
yeah.
Well, isn't the water used as a lubricant, we think, in the tectonic plate
It
movement?
will help because the minerals then being hydrous lowers their melting temperature, kind of like putting salt into water
Right.
here on our streets. So it's the same kind of thing, but most of the melt occurs in the mantle because you're letting off pressure, not because it's so hot, but it's hot, but now you're letting off the pressure as it rises, and so you get it melting.
Yeah.
Yeah.
Well, what about the origin of the water to begin with? I know there was been a lot of talk for decades about a comet or comets brought in water earlier in the history of the
Yeah.
Earth, and they look at isotopic ratios, so looking at the different forms of hydrogen, for example, to see if it matches. Sometimes it doesn't match, and other times recently we see, yeah, it does match. So we kind of flip-flop a little bit back and forth. So what's your feeling on that issue?
Yeah. It looks like comets may have provided about 10% of the water and other volatiles on Earth, but most of it came in with some of the meteorites that, accreted the Earth as a whole. And again, there are meteorites, various kind of carbonaceous chondrites in this that have a lot of organic matter, so they could give rise to a lot of the CO2 and things that we have. They have a lot of water. It's pretty clear that through some combination, and we can argue whether comets were 10% or 15%, but through some combination of Earth's accretion and early stage, both meteorites and comets, that's how we got our inventory of volatile materials.
And if that's the case, then we're not unique, right? Our location here in the solar system. So,
No, that's right.
yeah. So, I mean, I can think of other stellar systems, exoplanets, that there's no reason why they wouldn't also be subjected to, coming in of water that may or may not aid in the development of potentially life on those surfaces under the right conditions.
Well, even in our own solar system, there's every evidence that both Venus and Mars once had copious amounts of water from just the chemistry of their atmospheres and the geology, the geochemistry. So yeah, absolutely. There's no reason to think so.
And Venus is famous for not having, as far as we know, tectonic activity. So you don't have the type,
Well,
Or is it
that's not
just different
entirely clear.
or is it different from what we have, I guess?
Yeah, there are parts of Venus, and you guys may know more about this than I do, but there are parts of the Venus surface that has been resurfaced
Yeah.
in relatively recent times, which means there's probably volcanism of some sort. So it's not like, Mars is pretty much tectonically dead, I think, or at least close to it.
Close to it.
Venus, not so much. The trouble with Venus is it has this so-called runaway greenhouse effect, so that it's hot as blazes there, and Mars is too cold. And
Right.
and again, that brings up one more thing that people don't often think about when they think about habitable zones. A lot depends on the type of star that your planets are
Absolutely. Yeah.
revolving around. And so there are some stars that have radiation that would be inimical to what we think we know about life. We just happen to have a star that, it was great. It gave us enough heat to have liquid water on the surface. And then interestingly, the sun's radiation has increased through time, the luminosity of the sun. And you'd think that, wouldn't that just make Earth get too hot? But it turns out that there's an important control on the amount of greenhouse gases like carbon dioxide on Earth. And when it gets hotter, you have more CO2 reacting with water and then reacting with minerals to sort of etch them through weathering, and that keeps it's almost like a barometer for temperature, and that's an extraordinary thing and shouldn't be taken for granted.
That's the natural regulatory mechanism, if you like, for,
That's right. And the bad news, of course, is that in my lifetime, the amount of CO2 in the atmosphere has gone up by about a third, and the that's the time scale of CO2 and greenhouse gas increase that we're seeing today. The time scale for this geophysical mechanism is tens of thousands of years. So we're not going to get bailed out by weathering that quickly.
No, and you bring up a situation where some individuals will say, okay, let's go to Mars. Okay, now why do we want to do that? Well, you don't want to have humanity all in like your eggs in one basket. In case of a natural disasters, we should have people living somewhere else. And then you say, okay, what are we going to do on Mars? Because it's very inhospitable. You have to do a lot of things to survive there. Well, let's terraform the planet. You hear that word being used a lot. And I'm thinking right away is, you're the same people who don't think that humans have an impact on the climate here on Earth, and yet you see what I mean? Then you're all for this terraforming. I mean, aren't we terraforming the Earth right now?
And I will add,
Yeah.
people that suggest that terraforming is cost prohibitive.
Oh,
There's
yeah.
really no
Yeah.
feasible way of doing this. So it will always be that we're digging into the Martian crust, living in caves there or something like that. Same thing with the moon, you know. Maybe in another 1,000 years or so, we'll figure out a feasible solution. But yeah,
I just find it sad. I know you wrote about a lot of this, Andy, in the book that I read, The Brief History of Earth, but I just find it sad that we can't, and this is other stuff, as you know, and you don't have to comment if you don't feel comfortable, but I find it sad as a human species that we can't talk maturely, if I can use that word, about these grand issues like, climate change, whether vaccines are good, without jumping immediately into politics, and then everything, once you jump in there, somehow then all bets are off in terms of a reasonable discussion. And you look at the data. As a scientist, it's easy for us, of course, we're trained to be like that. We look at the data. You can look at a graph, looking at the abundance of CO2 and how it changes with time, and see it's increasing steadily. And if you extrapolate that, it's not a good thing.
right.
And all I really want, in some sense, if you boil down to the basic fundamentals of life, is I want clean air to breathe, I want water I can drink, and I want to go to the beach once in a while and not see pop cans laying all over the place. Is that so much to ask?
Yeah, no, you're right. Everything, particularly in recent years, has been politicized. I think there are people who see profit in extracting more fossil fuels, and so they don't want any limits on what they can do. And that's going to come back to haunt us to the extent that we do it, because we're extracting fossil fuels at high rates, and we're not making it at anything like rates that would replenish it on the time scale of human existence, let alone the 21st century. So we do need we need fossil fuels for certain types of materials in that, and at least I think that we would be better off actually investing in things like wind power, solar power, nuclear power. All of these things can generate electricity and heat without changing the amount of greenhouse gases in the atmosphere, and actually preserve some reserves of carbon for our grandchildren. So, I think, yeah, it is a little frustrating sometimes. You mentioned vaccines. It's the same thing. The science is in. It's not like this stuff is controversial anymore. And when, we live in a country that had eradicated measles
Right.
years ago, and now we have children dying of measles, there is a rational approach to this.
I think some of it is that there are certain politicians who jumped on the issue and based all of their conclusions on the models, the predictions, and those predictions didn't come to pass. Well, that leads people to go, oh, well, the science isn't there. The science is there. You just put all your eggs into a model that may or may not have been, you know. And I think that's some of the problems that have caused people to start questioning, well, science was wrong about that. The science wasn't wrong. You just believed a model that had incorrect assumptions. And, but these things are happening, So,
I always thought, Andy, when you think about it, I don't know if how much you watch TV or not, but there's, a local station that shows a lot of old TV shows from back in the 60s, back in the 70s. Mm-hmm. And occasionally you'll see one from back in the 70s and they'll show this sort of wide angle view of the city. It could be LA or Chicago. And because it's the 70s, you see like smog everywhere. And you're thinking, how could you live there? And then if you did the same sort of shot today with a camera, that smog is no longer there. And it's like, we can have a positive impact on our environment.
Right.
No question.
Yes.
It's amazing. And also when you think about like petroleum companies, wanting to make as much money as you can, don't you not want to kill your customers? Who's going to buy your product, right?
Yeah. Now, and it's fair to say that some of the industrial entities that are most behind alternative power sources are petroleum companies, because they're not stupid. They know they're going to run out of product sooner rather than later. And so they're investing in what they see, not us, but what they see as the energy of the future.
Yeah.
Right. And that is something a lot of people miss. They're heavily investing in this stuff, and they're just keeping it on the low.
Yeah.
Because drill, baby, drill, as they say.
Now, I'm going to change this totally in the new direction, just because I wanted to ask you this question. I never got up the chance to do this, Andy. So when you listen to documentaries, like I said, I'm not even close to being an expert in any of this stuff, not even an amateur. When you look at documentary about early humans, like what led to Homo sapiens, I see a lot of things that are done by anthropologists, for example, is the measurement of brain size, the cavity. Like you take a skull and you can estimate sort of where they are on the tree of life, if you like, by the volume of the brain itself. And that somehow, eventually you get to the point where creatures, whether human or not, are using their hands to make tools. That's a big significant sort of passage of time, rite of passage, if you like. But I never could understand that connection because, just as an example, I have two dogs. One of them is a golden doodle, and the other one is a cross between a Yorkie and a Chihuahua, which is obviously a lot smaller. And so I would estimate just by looking at them that the golden doodle has twice the volume of the brain than the other dog, and yet they do not seem to be any less intelligent each other, right? They seem to be about the same. So does that mean it's not just the volume of the brain cavity that's important for development of intelligence, but maybe even the density of neurons, like how they are compactified, if you like, in that enclosed space, and that as well as maybe some other things that we're not quite sure of, because obviously the brain, we don't fully know how it works. There's more than one factor involved that sets us apart from another form of life that you would say was less intelligent than us, for lack of better words.
Yeah, no, it's brain size is a fairly coarse measure of intelligence. It scales with the size of the organism. If you want to find organisms that have, sometimes twice as many neurons per cubic centimeter of brain as us, look at songbirds. And so I think, having a brain that could allow us to communicate, having hands that could do many things. I think all of those things are important. It's been argued, for example, that cooking food was an important milestone in that then people could move with food that's already been cooked and preserved and things like that, and you would get more nutrients out of it. And again, I don't think it's that all of these arguments are wrong so much as incomplete, that there's a lot of things that go on, and we are, the fortunate beneficiaries of those.
Yeah. Is it true that there could be, and I never heard this anywhere, I'm just speculating here, that there could be key fossil remains related to us? Like you think of Lucy, for example, but maybe things that are even older that would show evidence of another new primary branch, if you like, in the tree that leads more directly to us, or at least another route to get to Homo sapiens that we just don't know about because, of course, there can be many things that we just haven't come across yet in terms of fossil remains and so on from the distant past.
Yeah, I think one of the things that we've learned over the last 2 decades through new discoveries is that there's actually quite a few species on our branch of the tree. We all knew that there were, various things, Homo habilis and things like this, but there's probably 7 or 8 or more species of the genus Homo, which is our own genus. There's tons more earlier in time. It's quite possible that our direct ancestors have not yet been found.
Right. Now I have to I have to say something here. I have to admit to this. Okay. I just discovered recently, this is from 23andMe. I think they went out of business now. There's a new company. There is a very small percent of my DNA that's traced back to the Neanderthals. So I'm just warning you.
Right.
But that seems to be almost the case that's probably the case for every human being.
It is.
Yeah, pretty much.
Yeah.
Pretty much. I think the earliest humans in Africa, I'm not sure that they all have Neanderthal, but when humans went into the Mideast and up into Europe, they lived side by side with Neanderthals for many, many years. And, we now can get DNA from the bones of these individuals. And clearly there was crossbreeding between humans and Neanderthals. And then if you go over to Asia, you'll find that there is also some DNA from a poorly known species called Denisovians. And so the idea that there was no crossbreeding between these populations simply isn't true.
Right.
Yeah. I wonder how close your DNA has to be so that you could have children.
Well, viable children
Yeah.
becomes the issue. If it's far enough apart, you get like horse and a donkey, and you get a mule,
Right.
which even gave us that term. So
yeah, it's fair to say that these are not wildly different. They're not on wildly different branches of the hominid tree. That they are somewhat closely related. In fact, humans, Neanderthals, and Denisovians are probably each other's closest relatives.
right.
Now, would that strengthen your propagation as a species to have more of a mixture of DNA rather than being an isolated community, where you just have like a few hundred individuals or something?
That's a little bit hard to know. I think, generally having more genetic diversity within your population is a good thing. Whether that's the case for humans and Neanderthals, I couldn't tell you.
Yeah. Definitely interesting for sure how that all plays out. I mean, a lot of those experiments, you can't do them because they're inhumane, right? You're
Right.
not going to. Right?
Yes.
Yes, that's right.
And thankfully we realize
Yeah,
that.
it's like cloning, right? You have to be very careful when you talk about cloning.
I always loved the meme I used to see that what do you get when you cross a cow with an octopus? Immediate cessation of your funding and a visit from the ethics committee.
Yeah. Well, the good news is that, all of our close relatives like Neanderthals, like Denisovians, like other archaic species of the genus Homo, are extinct. So there's nothing, the closest thing to us now are chimpanzees and bonobos, and they're far enough away that I'm
Yeah.
not advocating the experiment, but I doubt that you would have viable offspring from that.
Yeah. Well, I mean, I'm not going to step on anyone's toes, but some people would say, they look at it. I remember being in a school that happened on a certain day of the week a long, long time ago when I was younger, and you'll know what I'm talking about in a second. And they would look at the students and then look at us. They were talking about evolution, and say, I don't know about you, but I didn't come from no chimpanzee.
Right.
In other words, they were put here as you are now by an entity, if you know what I'm saying here.
Yeah.
But I mean, the evidence is the evidence, and the science is the science, right? So that's one of the things we do. We try to piece.
And they're wrong in saying that, because yes, we did not arise from chimpanzees or anything. It's common ancestor to all of us.
Man, we share what? Is it 98% of the same DNA as a chimpanzee on average, or something like that?
It's fairly high, yeah.
Yeah, but then we share probably close to that with a sponge or something, there's more than
I think it's like 60, 65-ish% with, bacteria. So, yeah.
Well, what's most, in terms of intelligent, what's the most intelligent species on the planet? If you're not talking about, what's it, octopus and dolphins and these sort of things, right? So,
yeah, it's wide open field.
yeah, very, very interesting. In fact, we're coming to the end of the podcast, so thank you very much, Andy, for doing this. Really appreciate a lot of great information and a lot of fun chatting with you. Mm-hmm. And I encourage,
It was a lot of fun. Thank you.
Thank you. And I encourage those out there who are interested in these sort of topics that pick up some of Andy's books and read them.
Absolutely.
Because they are a great read for sure. And the other thing is, too, if you're like a young student and you want to go back, want to go to school after high school, come to places like the University of North Dakota. And you can take a lot of programs in both the STEM field and arts and so on. Geology, you can learn all kinds of these things. And you never know what happens in life when keep educating yourself. That's the motto I like to preach.
Right.
Now, at the end of every podcast, we always leave you with a quote or an excerpt from somebody's writing. And guess who I picked today, Robert?
I'm going to guess our guest.
That's exactly right. So if you bear with me, Andy, hopefully I don't mess this up. But this is a excerpt from Andy's Brief History of Earth, 2021. Don't forget, he has a brand new book, which I didn't have a chance to purchase yet, but I will as soon as I'm done with this. I'm going on Amazon and looking for it. So here's the excerpt. Understanding Earth's history helps us appreciate how the mountains, oceans, trees, and animals around us came to be, not to mention gold, diamonds, coal, oil, and the very air we breathe. And in so doing, our planet's story provides the context needed to grasp how human activities are transforming the world in the 21st century. For most of its history, our home was inhospitable to humans. And indeed, among the enduring lessons of geology is a recognition of how fleeting, fragile, and precious our present moment is. With that, please give us a thumbs up. Please subscribe if you haven't subscribed. And thank you very much for watching.
Thank you, folks. See you next week.
Thank you.